Navigating a dense city intersection at dusk requires an autonomous vehicle to see beyond its physical sensors. It utilizes a high-definition map, a virtual sensor that provides a pre-programmed digital memory of the environment far beyond its camera's line of sight. Before reaching a corner, it uses a stored geometric grid to identify traffic paths hidden around the bend. A fundamental problem arises when these two versions of the world, the digital record and physical environment, begin to diverge. This reliance on memory introduces a high-stakes variable. If the machine operates on an outdated model of the world, the safety of the entire mission depends on its ability to detect the discrepancy between its data and the actual asphalt. While the physical world is dynamic and subject to sudden chaos, maps are static snapshots frozen at the moment of their creation. A heavy rainstorm can wash out freshly painted lane markings in a single afternoon, creating an immediate rift between data and reality. This is the stale map problem. Environmental shifts, like the sudden arrival of construction crews or a layer of seasonal snow, can render the vehicle's digital knowledge obsolete and unsafe without warning. If the system defaults to blind trust in an outdated map, it may trigger phantom steering. The car could guide itself into a non-existent lane or steer directly into a physical hazard that wasn't there when the map was drawn. To prevent this, the vehicle runs continuous, real-time background diagnostics. It pits live camera and LiDAR feeds against the stored HD map, scanning for structural decay in the digital model. Success in a changing environment requires the AI to verify its own memory against the literal reality of the present moment. When the car's real-time sensors contradict its stored map, the machine faces a critical choice. It has to determine which version of reality is actually true. In conflict resolution, the system weighs the probabilistic uncertainty of both inputs. For static infrastructure like highway interchanges, the HD map holds a higher truth weight, providing stability. But for dynamic objects like pedestrians, live sensors are granted absolute veto power. If LiDAR senses a physical mass in the road, it does not matter if the map claims the lane is empty. The map is ignored, and the system executes emergency braking or an avoidance maneuver immediately. By maintaining this strict hierarchy of truth, the car ensures that the physical present always overrules the digital past. Beyond simple data conflicts, the system eventually hits a total informational blackout. This happens when the digital record simply terminates at the edge of a new development or an unmapped side road. This boundary is the Operational Design Domain, or ODD, the specific geographic area where the vehicle's safety is mathematically verified. Stepping off the map plunges the vehicle into Area 3, a zone of unknown and unsafe variables where its primary navigational logic fails. Since the system cannot guarantee safety in this void, continuing blindly into unmapped territory is strictly prohibited by its core software. As the vehicle senses the approaching edge of its known world, it triggers an immediate demand for a human driver to take control. However, the system must also account for the human failing to respond, or for vehicles that have no manual controls at all. This triggers the final fallback, the minimum risk maneuver. The vehicle gracefully decelerates, pulls over to the shoulder, and brings itself to a full stop. The machine is programmed to prioritize safety over its destination. It chooses to halt its mission to ensure it remains in a safe state. Advanced autonomous engineering prioritizes the preservation of life over the completion of a route. The system secures its most critical safety objective by detecting its own functional limits and choosing to stop